lecture in the AI for Geophysical Dynamics course. So today we're going to talk to you about links between deep learning and optimization. So there's going to be a first part of the lecture that will be given by Serge Graton, who is with us via Zoom. He's a professor at INP Toulouse and IRIT, and he's going to talk about how to use optimization tools for deep learning to optimize neural networks. And there's going to be a second part where I will be talking about how to augment optimization algorithms with deep learning techniques. And there's going to be a lab session about that as well. So without further ado, Serge is going to give you the basics of optimization for neural networks. So Serge, it's up to you now.
Thank you very much. So I hope everybody can hear me. And I will start. So first, I will present the general setting of learning. We shall see that there is an optimization process that is needed in this setting. And then my goal is to present is to go directly to my final slide, and my final slide is maybe one of the most famous machine learning optimization algorithm that you will find in any deep learning framework. So I will start first with some facts on learning in general. So the problem is the following: we have a set of data, and the set of data consists of AJ, YJ. So AJ is a set of features, YJ is a set of labels. And the idea is to understand and maybe to find the connection between AJ and YJ in such a way that if you have a new vector of features, AK, we are able to predict here its label. So we are able to find the function phi, which makes the connection between features and label. So this is generally what we want to do. And to do that, we write this problem in terms of an optimization problem. So the goal is to find phi, which is the argument of the risk of misclassification function R. So what is this risk? It's the probability that phi of A differs from Y. So I want to minimize this risk. And this risk can be easily written as an expectation as it is done here. And so if we have access to samples of the distribution omega, so the distribution omega is a distribution of AJ and YJ. So if we have access to omega, what we want to really to find is the minimum argument of R. In fact, usually we don't have access to omega, to the full distribution of data. We have only access to a sample of those data. And so we have access to AJ, YJ for for capital N number of AJ, YJ. And therefore, we propose to sample this expectation, so to sample this probability, and we are led to the minimization of this empirical. So it's an approximation of an average, of a mean using samples. So it's called, this quantity is called the empirical mean. And Rn is the empirical risk of misclassification. And so this is the first R of phi is what we would like to minimize, and Rn is what we can minimize using the sample that we have at hand. So the problem and an important issue in all what we do in machine learning is the risk of overfitting that occurs, that can be presented as follows. Imagine that you have access to capital N data. The Yj and Aj, we can define a function phi that takes exactly, so we define this function directly by telling what is its output for a given input y, as follows. So we associate to x, yj, the true value aj that we have from, because it's the data we have from sampling. And for any y that falls outside of our data set, for any y, we give any function for any a that is outside. We take any label for it. So in this case, this function performs a perfect fit on our sample data. So for any aj here in the sampling of data, we have this phi of aj equal yj. So there is no, in fact, pair of aj, yj that is misclassified. So the empirical risk is 0 with this particular function. However, this function performs extremely bad when you fall outside of the sampled data set. And this is something that we want, to, of course, to avoid. And I will present now in a few slides what is the theory behind that, behind this risk of overfitting. So this risk of overfitting, in fact, can be also described using the following theorem, which is called the no free lunch theorem. So this theorem gives a negative result. And I will explain what this theorem tells in a few seconds. So what we would like to have is a way to construct this classification function phi n in such a way that when n goes to infinity, phi n converges to the true phi, which is what we can write in this way. So we would like the limit of r applied to phi n equal to the minimum of r. And if this is the case, then it means that I can just solve my my empirical risk minimization, get a phi n, increase n, and I will converge to a phi that is, or I will have this, more precisely, I will have this result. This is really what I would like to have. Unfortunately, so this no free lunch theorem says the following. For any epsilon, so this will be a quantity which is expected to be small. For any epsilon and any n, there exists the distribution of data, so p omega, not a sample, a true distribution of data, such that there is a function that perform well. So there is a solution to my risk minimization problem, which is phi star. But unfortunately, any prediction which will be learned from a distribution data dn will be such that the true risk evaluated at phi n will be greater than 1/2 minus epsilon. So this result tells you that for any epsilon there is and any n, there is a distribution of data, and there is a function phi n, such that the classification will be very poor, because here remember that what you would like to have is something very small, but you get something which is 1/2 minus epsilon. So this result is tells you that in general it will not be possible unless you add additional constraint. It will not be possible to get this kind of result. So here you may find this example quite artificial, because the data distribution here depends on n, in fact. So it is changing along with your epsilon n, and there is a better result or more refined result here, in which it is not the case. So you choose a priori a sequence of say epsilon a priori, and then you choose a unique distribution of the data, for which unfortunately you will have the risk which will be greater than epsilon n. So it means that you can take here a sequence that goes to 0 extremely slowly, and in this case the risk will be bounded by something which goes very slowly to 0. So it means that you need a large n to get some hope of having a good classification function phi of n. Okay, so after this negative result, we come to the conclusion that we need to do something, and something to make our estimation problem meaningful. Something is either restrict the distribution of data that we consider, and this is called the generative approach, and I'm not going to talk about that today. Or another possibility is to restrict the class of function in which you are looking for phi. And this is the so-called discriminative approach, and this is the one I will be interested in. So if we now go back to the general problem, we have here, it's one, we have distribution of data. We have our risk, the exact risk of misclassification, which is called R. This is what we would like to find, this quantity, which is the minimum of R. And what we can do is to sample from this data, and usually it's a sample of data you simply have in your data set. And we suppose that you are able to solve the problem 2 here and get a phi n. Maybe this is already this poses already a question, because when I write here mean, I'm assuming that I'm able to find the global minimum of a function. And if you had a course on optimization, you may have learned that this is an extremely difficult task in general. So this is already the assumption that I can solve 2 is already a very strong one, and in practice we are very far from being able to minimize R of n. We are able to find maybe just a local minimum for this function, but finding the global minimum for Rn is something extremely difficult. So in practice, we will replace 2 by a simpler problem, which is finding a local minimum with some iterative algorithm. Okay, so 1 is what I would like to have, 2 is what I can have, and I would like to understand a bit more in connection with this no free-lunch theorem. I would like to understand more what are the limitations and how close I can get to the true phi using problem 2. So to do that, the standard approach is the following. So I want to get a phi n which is as close to phi star. So phi star is my true solution of my risk minimization. And the performance of such a phi n will be measured by using these inequalities here. And of course, my goal would be to have the right-hand side of this inequality as small as possible. So there's nothing really fancy here to get this inequality. Just introduce Rn in the middle, use the fact that phi n is a solution of the minimization problem involving Rn, which makes this quantity negative. And then I get this expression here. So if I want to have R of phi n of R of phi n minus R of phi star small, one way to guarantee that is to have these two terms small. This term here, the last term, is a so-called bias term, and it tells me how phi star, what is the difference between the empirical and the true risk function evaluated at phi star. So, and this, if you go back to the definition of Rn and of R, this is directly related to how well the empirical mean formula approximates the true mean. This is just about this. So the second term is just how can I approximate a mean using the empirical mean. The first term is a bit, it's again the same thing. I mean, the argument here is similar. It's the difference between R and Rn evaluated at phi, but now phi will be in the set of all the possible classification function and consider. So here phi could be a linear transformation, could be a neural network, could be, but it is a very specific class. And I want to bound this error using the sum of those two errors. So the first term, as I said, is related to the class phi. The second is related to the minimization, the approximation of the mean. And using theorems that are based on Markov inequality or Hoeffding inequality, it's possible to get, for any phi, it's possible to get this bound. So this is exactly what we want. The probability is that the empirical mean and the true mean are, the difference is below some quantity here is y minus alpha. So alpha is something which is going to be, it is expected to be slow. And here you see a convergence in 1 over square root of n. Here you have a log. So this means that this term is not very large in general. This is, of course, the term that goes to 0. It does not go to 0 very quickly. It's just 1 over square root of n. Unfortunately, this is not very fast, but it does the job. With this, you can prove that if n increases, you will have a convergence to 0 in this sense. Now, so this problem is the convergence of these to 0 is handled with Markov or Hoeffding inequality. Now let's go to the second term. So the term involving the sup here. And this involves understanding the worst case now, because it's a sup, the worst case of the difference between mean and empirical mean. And to bound this term, we use a measure of the complexity of our class of classification function. and it's called the VC, or what we need for understanding this complexity is the VC dimension. So the VC dimension of my set of classification function is the largest number of features. So these features are A, such that for any set of labels, there is one phi in the corresponding class that correctly classifies the features. So it means so what happens if you take too many? Imagine that you do linear classification. If you do too many, if you have too many features, it may be that there is not a label, a set of labels for which there is a phi. So there is a linear function that does the classification. Because of course your linear regression function phi depends on some parameters that define this linear transformation. And if you have more data than parameters, it may be that you cannot find a unique phi. And this is exactly what happens here in this linear case. So the case of the linear prediction. And here it is the parameters that you have in your prediction is a vector, it's a vector W that you have for your model. And it's also B, it is the so-called bias. So the number of parameters of your linear regression is n plus 1, n number of weights, 1 number of biases. And it turns out that the Vapnik dimension of this simple model is n plus 1. So number of parameters plus 1. And using so you have a more general result if you do polynomial regression of degree less than p. So here you have the Vapnik dimension associated with that. And using this Vapnik dimension, you can finally bound in the same way as the bias term, this term here. And you find now that you have the terms that we have seen before, and now there is this other term that contains now the Vapnik dimension. And so what is now required is that this term goes to 0. But you see that if you work with a given n, this term may be very important and may even dominate this term here. Okay, so now we can represent all this in a chart. And the chart is the following. So here I have the class of functions that I will use for my classification. C is a parameter that determines the complexity of my class. So it could be so it is an hyperparameter that gives how complex my model is. And I can draw the two curves. One is Rn and what is R. So what happens typically is that Rn goes to 0. And so this is when you increase n, you have the convergence of Rn of phi bar. If you consider now the true risk, the R, the typical behavior is that it will decrease and then it will increase. And the difference of those two then does not converge to 0. And this is related to the Vapnik dimension that we just saw in the previous slide. And what we want to find is a point in which we get the best of our phi bar. So here, so it's a point at which Rn is small, but R is not too big. So this is a compromise that we want to find. And in practice, this is called hyperparameter tuning. It's what you do when you play with your neural networks, or if you do if you go beyond linear regression and you take polynomial model, this is the game you play. You increase the complexity of your model, but you should stop. And there are trick, which is take some samples for performing the minimization and leave samples to compute an estimation of R, so that you can measure the discrepancy between those two curves. Okay, so now assume that this is done. We have now, we can safely minimize R of n, and now we are going to talk about algorithms to do that. Okay. So I mentioned linear regression as a way to as a possible way to compute a phi for performing the prediction of the target y. In fact, recently we have seen that a nonlinear regressor can be very good for many tasks. In fact, you probably heard the story that those nonlinear regressors have been known since more than 20 years. And it's a combination of progress in algorithms and also progress in computer architecture that makes them now very good candidate for solving many tasks of regression of classification. And those classifiers are, of course, neural networks. So, and a neural network will be a nonlinear function of the weights, and we have to find ways to minimize a function like this. So this is back our empirical risk minimization in the case where the dependence of the function in, for instance, the weight is nonlinear. If it is linear, we have many tools. Of course, if it is large scale, it can be difficult, but we have some tools to do that. But now we are considering that we are handling nonlinear function, or maybe a nonlinear function. For instance, R can be a neural network. Okay. So, I'm considering, for instance, as an example of a nonlinear function, a neural network. I'm sure you have seen what is a neural network. So you have input, and you have hidden layers, you have outputs, and you have weights, and this is a graphical representation of a neural network. It's just a graph. And of course, from this graph, there is a mathematical expression for phi. So here, I decided to label, so all the weights here from the different layers are written here, are put in a matrix, which is capital W, and the lower index represents the number of the layer that occurs here if I go from the left to the right in this neural representation. Okay, so I want to my goal will be to find the best value. If I go back to my empirical risk minimization, my goal will be to find the optimal value for the weight, so that the risk of misclassification, Rn, the empirical risk, will be minimized. So I'm just minimizing a function like this one, where now the weights here are the weights that occur in this neural network. I will not go further into the structure of neural network because Luca told me that you had already seen that backpropagation and things like this. So I assume from here that you know what a neural network is and that you know that it's possible to compute the gradient of Rn with respect to the weights capital W here, that are in the network here. So one way to minimize, so now my function will be denoted by f, the function I want to minimize. So this can be, f can be my empirical risk Rn, and x, as I said here, x here is the set of weights that I have in my neural network. So I want to minimize such a function here, and let's review ways to do that. Maybe the simple way to do that will be just to resort to a gradient method for continuous differential function f. Luca will present you situations where the function is not necessarily differentiable, where you have a sum of a differentiable and a convex, possibly non-differential function. But let's start with the easy case here. So what is a gradient method? A gradient method takes a step alpha k in the direction which is opposite to the gradient. Alpha k is the so-called step size. And here I'm just using this rule to compute the next possible value of my weights, because if you look at the Taylor expansion, you will see that if you look at the first order Taylor expansion, the negative gradient direction is a very good direction to decrease your function locally. Remains to find, of course, the step alpha k, but there are very good mathematical reasons for taking the negative gradient. Now, what happens if you do that? You need, so alpha k will be positive because you want to go in the direction of the negative gradient direction, but it's not enough to have a convergent method. Defining your iteration like this may lead to the following situation. So here I have a quadratic function, and here, if I start from the point here labeled +5, if I take the negative gradient direction, so here, if this is x squared, the derivative to x will be negative here. So if I take the negative gradient direction, I go right here, and you see that depending on the value alpha k, I may stay in the region close to the function here, square root of 5, or I may go in the other part of the parabola. It is a bit awkward to go in the other part of the parabola because my optimization algorithm is defined using first order information. So I'm using the local behavior or the gradients derivative of my function to define the next iterate, and here I go in the direction and to the point where I'm not relying anymore on the tangent of the function at square root of or minus square root of 5. So here my idea was to use a gradient method, but my step is very large. And in fact, what could happen here is that I could even not converge to my solution if alpha is too big. There are examples, where if alpha is too small, you don't converge either. So finding an appropriate alpha is something very important. And a trick that has been used in the years is to find a value of alpha that achieves a sufficient decrease of your function, which is measured by this kind of inequality. If you have some information on your function, for instance, if the gradient of your function is Lipschitz continuous, with a Lipschitz constant L, then if you take a step alpha, which is equal to the inverse of the Lipschitz function, using first Taylor inequality, which uses the fact that the gradient of f is Lipschitz continuous, you get this majorization of your function in terms of alpha. And playing here with those terms and replacing here, noting that the direction is gradient of f, you get here a gradient square here. So you get this term here. And if you just plug the value 1 over L in here, you get that at each iteration, you get a decrease of your function. So f of xk, f at the current point minus f at the next point is greater than the 1/2 of the Lipschitz constant multiplied by the norm of the gradient squared. And now the easy way to show that the algorithm converge is to sum all these inequalities. And since this will be bounded by if you sum all this inequality, here you have f of xk minus f of xk plus 1. So if you sum all the right hand side, you get first point minus final point, and on the right hand side you get sum of the gradient squared. And it turns out that first point minus last point is bounded if your function is bounded. So this is always bounded if f as a minimum or is bounded from below, which means that the sum of the square of the gradient, which is a series of a positive number, is convergent. And this says that the term of the series, which is gradient, is convergent. So just a first order method, if you know the Lipschitz constant is something that converge. Here you see gradient squared, and this is important. This tells you that if you want to reduce your gradient below epsilon, you will need a number of iteration, which is 1 over square root of epsilon. So here it's what I just said. So telescopic sum tells you that. And and then from this, I get the minimum value of the gradient in the first k iteration is bounded by this. So if I want this to be less than some value epsilon, I need this to be less than value epsilon, and I get a convergence which is in 1 over square root of k, or a convergence. So this is the decrease of the gradient along the iteration. And if I want to achieve a gradient of level epsilon, I need at most 1 over epsilon squared iteration. Here I just put this less than epsilon, and I get 1 over epsilon squared iteration, which is a typical complexity bound for unconstrained optimization, 1 over epsilon squared. So this rate of 1 over square root of k is not indeed very fast. Your method, so in your method, you need to compute the full gradient of your function, and you get a convergence rate of 1 over square root of k. It's not a very good rate of convergence because we know that it's possible to have a much better convergence using other tools, like, of course, Newton method or quasi-Newton method. Maybe you have seen those algorithms, but unfortunately, this method require some access to the second order derivative of function f, which may be quite expensive to get in practice, especially when you're playing with large neural networks. So there is a lot of research on trying to find how to use second order information in deep learning, but at the moment people are not using them in practice. They rely more on first order methods. Okay. And with Luca, we'll see the case of the optimization of a sum of two functions briefly. Okay, so gradient is good, gradient iteration, but it's possible to get, and it's possible to show that in the convex case, you have a convergence of 1 over k instead of 1 over square root of k. So if your function has has better properties than just being differentiable, if it is convex and differentiable, then the first order method will converge with the speed 1 over k, but it's possible to have something much better. It's 1 over k squared. And to do that, the idea is to use a so-called momentum term in the first order method. So what is, so it is based on an analogy with mechanics. And so this is basically the discretization of the derivative of x. If you imagine that there is a continuous time process behind the computation of x, and by adding this term and tuning properly beta k, you can have an algorithm that converges much faster. Of course, my goal here is not to present you all the theory behind that, but you may have seen that you can use gradient method with momentum in PyTorch, for instance. It's called SGD with momentum. And what the method does in this case is simply something like this. The first order iteration is corrected using this term. And in the convex case, you get a very good convergence, and this is implemented in the non-convex case as well. There is an algorithm that has been made very popular by Nesterov in '93, which is again based on the idea of the momentum. The momentum is placed here in two places. One is inside of the gradient, and also here the momentum term, which I just described. This scheme is written more compactly in this way, and this is definitely a better algorithm if you have a provable better algorithm in the case of the minimization of a smooth function, and it is used in deep learning for even if the function is does not have a lot of property. So this is the acceleration, the momentum in the acceleration. And here you find the way that you have to define beta k to get the good convergence properties. Is defined by this sequence. Excuse me, are there questions?
I don't think so.
Okay, sorry. Perfect. So one important feature for first order method is this idea of acceleration, and for which it's possible to prove that you get much better rate of convergence. Another idea which is very important is the idea of using stochastic gradient. For the moment, I was using the full gradient of my function here to define my iterates, and now we will use a stochastic variant of this algorithm that is described in this way. So remember that we want to minimize this risk of misclassification, and we have only access to this empirical version of it. So we don't have access to the full function, and we don't have access to the full gradient as well of R. We have just access to the gradient of Rn, for instance, right? So in the stochastic gradient method, the idea is to replace the function. So first is to say that I will choose in this sigma here, I will not necessarily work with all the n values here. I will choose some terms from the sum, and I will choose them randomly. So I introduce a random variable that will choose a certain number of terms here in my minimization. And this function is xi. So xi represent choosing some terms in this. So I will take samples from my data set and replace in my gradient method f by an expression where I don't will use all the n available data, but just a subsample of those n data. So I have the continuous R, which involves the true expectation over all my data set. I have Rn, which involves now all my available data set of size capital N. And I will now consider an algorithm where I will consider even less terms, not capital N, fewer terms. And this will provide me this stochastic gradient method that traces back to Robbins and Monroe in 1951. It is just this method where I replace Rn by just one, the evaluation of the gradient of just one of those fj, and j is chosen randomly, and this is denoted here by jk here, which is randomly generated from 1n. So this iteration is much cheaper, of course, than the full gradient method I've been considering so far, because here I only consider I only compute my gradient using one sample of my data. The analysis of this algorithm is a bit more complicated because now I have some randomness, and this make my method now a stochastic gradient method. And some elements of the convergence theory are a bit more complicated because I don't have remember that previously I was using the decrease of the function and performing the telescopic sum. So now, unfortunately, with this randomness, I cannot guarantee that all the samples from this iteration will induce a decrease of my function. It may be on average, for instance. And so there are several methods that I can consider. The full gradient, batch gradient, in which I do that, or there is the sample version in which here I just use one sample to perform my step. So this is much cheaper than this one. And okay. So why should I use? Why do I have any hope that with using even less term in the sum, I can have good results, or I can have an efficient minimization? And this is the point. If I consider the decrease of my function along iterates, what will happen here if I use this? So this scheme is more expensive than the Robbins and Monroe stochastic gradient, because here I have to compute all the gradient and sum them all. So this may converge faster, but the cost per iteration of this method is much higher than the previous one, because here I have to compute n gradient. So it is n times capital N times a more expensive for at each iteration than this much simpler simpler scheme. So why do I believe, or do we believe, or do people believe that it could be good to use the stochastic gradient method? So if you do machine learning with your images, for instance, you probably have more than one picture of a cat. I want to classify cats and dogs. I probably want more than one picture of a cat. I have several of them, and I use this redundancy to make my learning process meaningful. So if there is some redundancy, maybe I can select here among all those terms. I can select terms that limits the redundancy and still give a good approximation. Remember that this is a mean. The 1 over n sum of something is the mean, and if in my mean I have many samples that are rather similar, I can, in the mean, I could replace this similar sample by only one of them. It's hard to do in practice, and we don't want to make this clusterization a priori, but this gives us an insight on why working with a subsample of this capital N may be useful. It's just because there is some redundancy. I want to estimate a mean, and so I can probably just find some individuals that represent the mean. This is one way to and the other way to understand why stochastic gradient may be useful is that is now more empirical. If you look at the convergence, typically with a stochastic gradient, you make a very fast improvement after 1 or 2. So an epoch is when you go along all the data. So a stochastic gradient is very fast at the beginning, and then it stabilizes. And maybe when it stabilizes, you have already a good approximation of your phi of n, because remember, what we don't want to minimize is we don't want to minimize r of n, but r, which is a continuous guy, and so maybe it's enough to rely on the fast initial improvement of the stochastic gradient, and then you probably reach some value, and maybe you cannot go much below it with the stochastic gradient due to these samplings that you perform at each step, which introduces some noise, but maybe this is already satisfactory for your prediction task. And this is typically what happens with a stochastic gradient. You have a quick decrease, and then it stabilizes. You can with some techniques, you can probably improve a bit over this, which is this plateau, which is due to the noise that occurs in the method. You can improve it, but this is typically what happens. So this means that the true empirical risk is decreasing typically very fast with the stochastic gradient. And remember that per iteration, the cost of the stochastic gradient is very low. So you get here a very quick decrease as a very low cost. Okay. So this you may several people have tried to analyze this plateau, which is, as I said, due to the noise in the method, because you never have access to the full gradient of Rn, and even worse, you don't have access to the gradient of R neither. So a way to explain a bit this this noise is that, and this was proposed by Bertsikas in 2015, is that when you pick up terms in the series, And if the sum is the sum of functions, here I represented quadratic function, changing j means moving from one parabola to the other. And an explanation for the behavior of stochastic gradient is that after you get a good initial decrease, you may be messed up in this set of parabola and moving from one to the other. Okay, so this is a stochastic gradient. You may this is stochastic gradient. You can do something which is called a mini batch stochastic gradient. In mini batch stochastic gradient, you take something intermediate between choosing only one term for computing the gradient and capital N terms. You take B terms, cardinal of B terms here. So you choose not one index, but you choose a sample of indices on which you compute the gradient. So typically, B is the mini batch where you will pick up your index for computing your gradient. So typically, B is much less than N, could be typically 250. We take usually a power of 2, 1024, something like this. And it is usually much less than the samples when than your data set size, which is capital N. So it is much less. So it is intermediate between stochastic gradient, pure stochastic gradient, and the full gradient approach. Due to this additional averaging, the method usually is less noisy. And but it has a cost. Of course, the cost is that you have to compute more gradients and store more gradients in your memory. But the current trend would be to take as many indexes in B as you can afford with your computer memory. So usually people are really filling their memory with and taking BK the largest possible to reduce the noise. Okay, so now as promised, I will, so this is my final slide, and this is pretty much state of the art for a first order method for machine learning. So it's called the Adam algorithm. And I will just describe what is behind. There is a convergence theory on this algorithm. It's a recent paper by Francis Bach, Léon Bautou, Alexandre Defossé, and Nicolas Ursunier. So there is a recent paper that explain the convergence of this, not only of this, but of several variants. But Adam is definitely an algorithm that you should try if you are using PyTorch, say, for your machine learning task. So let us describe what's behind Adam. So the main step is this one. So here you recognize a first order method, xk plus 1 equal xk minus alpha k something. And m is a momentum term. So here you pick up in your mini batch, you pick up here, so this is a gradient of your mini batch. You compute this mk by using the previous one with some forgetting factor beta 1, and you add the current gradient of your current mini batch here. So this means that you are performing a moving average of your gradient. So this is the momentum moving average with beta 1 is an exponential decay of your gradient, because next time mk will be multiplied by beta 1. So you see in the recurrence that the importance of this gradient will be multiplied by beta 1 at each iteration later than k, and since beta 1 is less than 1, the importance of this term in the momentum will decay as beta 1 to some power. So this is making old term less important than newly or fresh evaluated gradient. So this is your momentum. You can imagine this as an average of your gradient mini batch, of your mini batches that are encountered along the iteration. So this is MK. And an easy iteration, which is a stochastic gradient with momentum, will be xk plus 1, xk minus alpha k, mk. But you have also this additional denominator here, epsilon plus vn. And this is a term that is added to decrease the steps in some directions. How is it done? In V, sorry, this is a K. So in VK, you sum the gradient squared. So VK is a function, it's a vector, but each entry of this vector is an increasing function, because each time, so if you take, for instance, beta 2 very close to 1, this has the trend to increase, this term here. So you divide entry-wise your momentum with this term here, which is if beta 2, it's the easiest way to interpret it. If beta 2 is close to 1, you have a decrease of your here of this scale direction. It means that your method is in fact, in addition to alpha k, it is further diminishing the step, and the idea is to suppress this plateau here. It can be seen that if you reach such a plateau and decrease the value of your step lengths, you can further decrease your function. And this gives rise to a lot of possible algorithms which are tuning the step lengths along the iteration. But this is one way to do it. It's what is done in Adam. And if you use Adam in PyTorch, say, so you use the momentum idea, and you use another idea, which is by this entry-wise division, you will automatically change your step lengths in each direction. And this is pretty much for the time being is probably an algorithm that you should choose, and you may do some hyperparameter tuning and choose beta 1 and beta 2 so that you get the best possible performance on your method. Okay, so I think I'm done here with what I wanted to tell you today. So maybe just a quick summary of what you have done. So the machine learning problem is finding a phi that minimizing some risk. You have only access to a sample version of this risk. Theory of learning is telling you that you have to be careful, you have to be cautious in the way you choose your the set in which you are looking for your phi, and then this being done, you know that it makes sense to solve a minimization problem. Up today, the most efficient methods for this are first order methods. It's not the case in general. If you were to solve another optimization problem for structural mechanics, for instance, or another area which is not stochastic, where you don't have this idea of sampling, maybe first order method would not be the best, but in this case, they are in practice the best. And among the first order method, the one you should have heard of is Adam. Adam implements here a momentum and this step reduction. And with this you get usually good result upon some parameter tunings that you can do further. And there is some theory, as I mentioned, Defossé, Bautou, Bach, et Husunier have a recent paper on how to understand the convergence of such methods. Okay, so thank you very much for your attention. And if you have questions, I would be happy to answer them.
Many thanks, Serge. So as you said, if there are any questions in the room or remotely via Zoom, don't hesitate. Otherwise, I suggest that we take a 15-minute break before moving on to the second part of the lecture.
Perfect.
Thanks. See you in